Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am super happy to have Siddhartha Gupta with us today. Hello, Siddhartha.
Hi, Frank. Thank you very much for the invitation. I'm very honored and I'm really excited to talk about our paper with the audience of this channel and with you. Yeah, thank you very much for the invitation.
Well, you're so welcome for agreeing to talk about your very lovely article, which we'll get to here in a second. Siddhartha, what's your geolocation? Where are you at?
Yeah, currently I'm at Princeton University. I'm a postdoctoral research associate,
Cool.
and I'm talking from the Department of Astrophysical Sciences from Peyton Hall and Princeton.
Is that because it's super hot outside and you're not doing it outside? Is summer happening?
That's one of the reasons. Yes,
Or it's more the humidity more than anything else on the East Coast.
absolutely,
Really more the
absolutely.
humidity and the heat. Here in Phoenix, where I am on this July 2nd of 2024, as we record this, it is a good and toasty. We'll probably hit the 110s today, so 41, 42 C, somewhere around there, off the top of my head. um, so yeah, summer's in full swing. Very cool. And how long have you been at Princeton there?
Yeah, so I was a postdoctoral research associate at the University of Chicago,
Oh, very
and
cool.
last year September I moved to Princeton University for my second postdoc. Yeah,
Oh, congratulations. Very nice.
thank you very much. Yeah.
And Siddhartha, what is it you like to do for research?
Yeah, I generally work on non-thermal particles, which are known as cosmic rays. So I study the mechanism by which the cosmic ray particles are accelerated, how
Cool.
do they propagate through the plasma, and what are their back reaction and how they control the evolution of galaxies.
Very cool.
And to study this, I use numerical simulations, analytical work for a better understanding of our observations.
Very cool. Very cool. And that is going to bring us to this very awesome APJ article. It is open access. It's the open access era, people. You can go get a copy for free. Go get one. Return currents in collisionless shocks. And Siddhartha, take us away.
Yeah. Before diving into the discussion, I would like to thank my collaborators, Damiano Caprioli from University of Chicago and Anatoly Spitovsky from Princeton University for giving critical comments in the preparation stage of this manuscript, which has improved the quality of this work significantly. So I really thank them for their contribution.
Great shout out. Great shout out. Okay.
So in this paper, we have addressed one of the very important question that how return current produced in collisionless shocks.
Okay.
Now, by collisionless shocks, we mean that the shock is formed due to the collective interaction between charged particles and the electromagnetic field rather than the Coulomb interactions between the charged particles.
Okay.
This is a very reasonable assumption in most astrophysical environments
Mm-hmm.
because in most astrophysical environments, the Coulomb mean free path is much larger than the length scale of the interest.
Okay.
So systems are very collisionless. Now, to give you the broad context of this work, I would like to recall that we all know in our universe, um, which can be our solar neighborhood or interstellar medium or intercluster medium or intergalactic medium, is made of hot ionized gas.
Yeah.
And hot ionized gas has two main ingredients. One is electrons, another is positively charged particles, which we call ions or proton.
Yes. Okay.
Now, if we, in most cases, if we take a small portion of our interstellar medium and if we plot the velocity or momentum distribution, then we will find that the distribution is very close to the Maxwell-Boltzmann distribution.
Okay.
And that's why we call it thermal plasma.
Yes.
But beside this thermal plasma, we also have a energetic charged population, which
Yes.
is known as cosmic ray population.
Yes.
Now, when we study the evolution of a plasma or a dynamics of a system associated with plasma, we make two fundamental assumptions. One assumption is that plasma is quasi-neutral, another is plasma is charged current neutral.
Okay.
Now, these are very basic assumption and it also makes sense because if we have a small cube and if it is filled with thermal particles, their motions are random, so they will not produce any current in the system.
Yes.
But if you have very energetic population, which is non-thermal population, they are very energetic, so they moves very fast.
Yes.
So when charged particle moves, they produce current, and you expect there you have some sort of current in that kind of system. Now the
Okay.
question is how thermal plasma responds to this current.
Ah,
Now this kind of setup can be seen in many places in our universe. It can be, as I mentioned, in interstellar medium, intergalactic medium, or intercluster medium. But for this particular work, we have focused on collisionless shocks
okay.
because it is well known that in collisionless shocks produced a strong current subconsistently. And that current is actually very important to drive self-generated plasma instabilities in the system.
Yeah.
Uh,
Okay.
so the question is that how upstream of a shock compensate this current, and what are the signatures of this current compensating population?
Okay.
Now, to understand this question, we can classify the shock in two categories. So one category shock is uh, called quasi-parallel shocks.
Yes.
By quasi-parallel shocks, I basically mean that the inclination of the shock normal, the direction along which the shock is moving,
Mm,
uh, and the inclination of the upstream magnetic field makes an angle less than 50 degree.
okay.
But so this is called quasi-parallel shocks. But there is another category of shock which is called quasi-perpendicular shocks, where have inclination larger than 50 degree. Now,
Okay.
this classification is extremely crucial because depending on the inclination, the, the population which is driving the current in the upstream of a shock,
Mhm.
that can be either electrons or can proton.
Sure.
So for quasi-parallel shocks, these are mainly protons, and for quasi-perpendicular shocks, these are electrons.
Okay.
So
Cool.
in that case, we have some current imbalance in the system. Now, if we want to compensate this current, there is there are two possibilities. One is the background plasma can drift, and when the background plasma drifts, they can actually compensate the current.
Yeah.
Or you can have a dedicated population of of the species, some with opposite sign, which can move along with the charged particles or opposite to the charged particles to
Yes.
compensate it. Now,
Yes.
in this case, we expect this population, which compensate the current, probably electrons, because electrons are much lighter, so they can quickly respond to the current. So you expect these electrons. Now, the
Yes.
question is, are these shock reflected electrons or they are produced locally at the shock?
Okay.
It's a very fundamental question, but so far this has not been addressed in the literature. So we address this problem,
Cool.
and to study this, we did self-consistent plasma simulations
Hmm.
and use a particle in cell code, which is a very standard approach.
Yep.
Uh, Now, if I go to the result of this paper, but before I go to the result of the paper, I would like to say that this paper is actually can be classified into two parts. So in the first part, we performed shock simulations, try to identify this return current population,
Yes.
and we also try to identify the mechanism by which this return current population is produced.
Yes.
And then in the second part of the paper, we perform control simulation to mimic the environment of the shock, but to get insights of the back reaction of this return current population,
Ah, okay.
so that we can quantify this the effect of this return current population.
Okay.
Now, if we go to section two now.
Yeah.
In the section two, we discuss the setup of our peak simulation. So we
Mhm.
start with, so we ran 1D simulation, which has spatial coordinates are 1D, but each velocity, electric field, and magnetic field has three components. So it's basically it's 1D 3V code.
Okay.
So we use a Tristan MP code, which is a massively parallel 3D electromagnetic code. Uh,
Hmm.
so what we have 1D domain, which is filled with electrons and protons, thermal electrons, which has a temperature, equal temperature at T equal to 0. Now, since we are interested in quasi-parallel shocks, we need to apply a magnetic field. So we chose uniform magnetic field based on our choice of inclination.
Okay.
Uh, and then we want to launch the shock in the system. So we use a moving piston which moves from left to right,
Yes.
and that sweep up the plasma and they produce shock.
Yes.
Now, if we go to figure one, we can see the shock profile uh, in figure 1A.
Yeah.
can see this is the density profile after certain time, and the horizontal axis of this figure is the distance
Okay.
in panel A, B, C1 and C2 and D1 and D2. We have the same the unit of the horizontal axis, which is like X, which is normalized with respect to ion skin depth.
Yes.
A
Okay.
very standard normalization in big simulation. Now, if you look at this figure carefully, we can see that there is a, downstream region, and then there is a upstream region, and the red dashed line that shows you the location of the shock.
Cool.
In the upstream region, there are various levels. Each of these levels basically shows you different region of the shock. So if you are very far upstream of the shock, you see the density profile is almost uniform. But as you move close to the shock, you have a precursor region where you have some ripple, and then in the close to the shock you have a region called shock food. So I will discuss why we call it shock food.
Okay.
Now, if you go to figure B, I mean, there's the below panel,
Yeah.
which we have two kind of curves. So the black curve that shows us the velocity profile.
Yes.
And you can see that in the downstream region, the velocity is close to 0.2 c.
Yes.
And in the upstream region, the velocity is close to zero. And that is because we ran the simulation in the upstream rest frame. So we expect the upstream velocity to be zero.
Okay.
But in the downstream, we see something velocity which is close to our piston speed.
Interesting. Okay. Yeah. Hmm.
And one of the interesting feature, if you look at the sine curve, which shows you the inclination of the shock with respect to, I mean, the shock inclination,
Yes.
then at the far upstream, the inclination is close to 30 degree, which is the same as we fixed in our simulation.
Okay.
But as we move close to the shock, we see that the inclination is actually changing.
Yeah.
And that is because of the self-generated plasma turbulence. We do have a better understanding like how exactly this instability work. And it turns out that it is driven by this energetic population in the system.
Cool.
Now, by looking at figure A and figure B, we cannot uh, get much idea about how the non-thermal population look like. Now, for a better understanding of different population, we need to plot the phase space distribution. And this is exactly what I showed in figure C1 and C2.
Okay.
Uh, that shows you the phase space distribution. So C1 stands for proton, and the C2 figure stands for electrons.
I'm with you.
In the downstream, I mean, in the vertical axis shows you the three momentum, the mod of the three momentum, and horizontal axis is the distance. Now,
Yes.
in the downstream of the shock, you see that thermal population, low energy population, and high energy populations are very continuous, right? So this is the downstream of the shock.
Yeah.
But upstream of the shock, you see the low energy population, which has a lower momentum. Uh, so they are much different from the high energy population. So
Yes.
the low energy population represent thermal population, and the high energy population that represent the energetic non-thermal population. So
Okay.
this is for protons. But for electron, we see the similar thing. So we have a low energy population, then we have a high energy escaping population, but on top of that, we also have a suprathermal electron population, and how the suprathermal electrons actually produce. This is what we're going to talk about in this article.
Very cool. And
If
what are
we,
what may I
yeah,
ask, what are the blue and red vertical lines in these figures?
yeah. So the in figure D1, we show the spectra of this blue region
Okay.
and the red region of this plot. Um,
Ah,
and
okay. I'm with you.
yes, marked in that region.
I'm with
So
you.
the solid line shows you the electron distribution, and the dash dotted line that shows you the proton distribution.
Okay. Okay.
Look at this blue curve, blue solid curve, that shows us electron distribution. And so we have the two kind of distribution. One is close to Maxwellian distribution. So Maxwellian distribution is highlighted by the black solid curve.
Yeah.
And then we have a slight hump, which represents superthermal electrons. And at the very high energy tail, we have a top hat profile, which represents the escaping electron population. For proton, we see something very similar, but we do not have a superthermal population in case of proton. But
Yeah.
we do have superthermal proton population if we go very close to the shock, that is shown by the red dashed line. We have some population where we have a continuous change from thermal population to the superthermal population.
Okay,
Yeah.
cool.
So until now, we understood there are different kind of population, but we still don't know that which population carries current, right?
Yes.
So to understand this current of different population, what we did uh, a velocity analysis, and if we plot the phase space distribution for velocity, this is how it looked like, which is shown in figure E1 and E2.
Cool.
In figure E1 and E2, that's the same curve. It looks very similar to them, but it now the distribution is color coded with the velocity, which is shown in the right color palette. So you can so the top panel is for proton, and this is the lower panel for electron.
Got it.
And in the upstream of of a shock, which is shown by this distribution,
Yes.
you can see that the velocity of the upstream thermal population is almost close to zero.
Yes.
Whereas the energetic population, they fly over the upstream, right? So you expect that there's some kind of current which is driven by this energetic population.
Indeed.
Yeah, and then in figure E2, you see the similar thing, but you see very dilute electron population at a very high energetic, because
Yes.
these are like very dilute population, maybe not properly visible, but you can clearly see there is a superthermal electron population which moves away from the shock.
Yes.
Now, if we integrate over the vertical axis, like which represent the momentum,
Okay.
then we can find the current, right? And the current is shown in figure G. So if we integrate over all momentum beams, we can find the proton current that is shown by this brown curve and the gray curve. And the brown and gray, they fall top of each other, which means that the total current in the system is exactly balanced um, uh, in the brown curve. And so we cannot actually see the brown curve properly because they are actually on the top of each other.
Yes. It's
But
steep.
the interesting point is that, so this is the total current. So total current in the system is balanced. But if we can estimate the partial currents, the partial current, I mean that if we can estimate the current in the high energy proton population and plot them, we will find that that current looks something similar to this orange curve.
Yes.
And the blue curve that shows you the population which carries the electron current. This figure actually shows you that the energy, the current in this high energy proton population is comparable to the electron population up to certain distance, and then you have electron current at very, very far upstream because electron just escape at the very far upstream region.
Cool.
Now, this figure clearly tells us that the plasma readjusts in a way that it compensates the total current.
Yes.
And we also saw that there is a superthermal electron population. So next section, we discuss how these superthermal electrons are produced. Now, to discuss this, we chose two different regions. One is far upstream region and the shock foot region.
Okay.
And we chose these two regions because these two regions has a very unique properties of this ion traveling population.
Okay.
Now, so what we in our analysis, what we did is that we chose a very far upstream of the shock when there is no current,
Hmm?
and we try to understand how plasma responds when the current reach.
Mm-hmm. I'm with you.
So, yeah, please, yeah, yeah, to and in current reach. So to understand this, what we did, we chose some tracer electrons and protons in the very far upstream,
Okay.
which are initially thermal. So we have thermal Maxwell-Boltzmann distribution for those particles.
Yes.
And then we track them with the time and try to understand how that distribution evolves at a late time.
Yes.
Now, if you go to the figure 2, that summarize the main outcome of that analysis. So in figure 2, at the top panel, the panel A1. So before I say anything about this figure 2, I would like to say this is three different snapshot at three different times.
Yeah.
So the first snapshot, A1, that shows us the very small portion of our simulation box. So we have thermal distribution, we have energetic population, distribution, which has not reached the upstream yet.
Yes.
And in the panel B1 and C1, we have a tracer electron distribution, which is shown in this panel. And you can see that tracer electron distribution is close to Maxwellian, shown in figure D1. So the blue curve in figure D1 that shows the electron distribution, and the red curve that shows the proton distribution at very far upstream electrons and protons, I mean, when there is no current.
Yeah.
And the panel E1 that shows us the Fourier analysis of electrostatic mode in the shaded region of this panel. Now, this is at a time when there is no current. I mean, the current has not reached in this the gray shaded region. Now,
Right.
in the later time, in the next snapshot, which is shown in figure uh,
Segment.
A2, we see that the current has already reached in this region. And we can see there the electron distribution is now started changing. But
Yes.
the proton distribution does not change much, which we can see from figure D2. And we will also notice that in figure E2, there is electrostatic mode has appeared. Uh,
Mm.
and this electrostatic mode can be understood by considering that if you have a plasma, if you have a beam, you expect some kind of electrostatic mode. And we have given the expression of this electrostatic mode in equation 3.
Yeah.
Um,
Yes.
uh, and the detailed derivation is shown in the appendix of this paper.
Cool.
Uh, and it's sort of consistent with what we expect from our analytical prediction.
Okay.
Now, at a later time, if you look at figure A3, we see that the current is now already moved into that region,
Again.
and we see that the electrons are, I mean, now become very, very hot, which you can see from figure D3. So we have a blue curve, which represents the electron distribution, and you can see there is the superthermal hump, which is very similar to what we saw in our shock simulations
Yes.
in the first figure.
Correct. Yep.
So this clearly tells us that these superthermal electrons are produced locally in the upstream of the shock.
Okay.
An interesting thing is that it is due to this electrostatic mode, which first driven by this beam, and then it transfers the energy of the electrostatic mode to the background, and background here take the energy.
Good. Okay.
Now, as time evolves, the plasma exposed to this current for a longer time, and the whole system is actually will develop slowly. It will develop electromagnetic turbulence in the plasma, and we do see some signature of the development of electromagnetic turbulence from B3 and B and C3,
Yeah.
where the background curve, the blue background curve that shows the magnetic field, and we see there is a some development of electromagnetic field. Uh,
Mhm. Cool.
so the idea is that when the beam penetrates through the plasma, it first develops electrostatic mode, then slowly with time it develops electromagnetic modes,
Okay.
and it will have a lot of fluctuation in the magnetic field.
Yes.
Now this is at very far upstream of the shock.
Cool.
Now, we in the close to the shock, we will see a similar result. Now, if you go to figure the 3, we will see in the close to the shock, we will also have a current imbalance,
Yep.
but now the current is very dense. So in panel A and B, that we show a very small portion of our shock, and you see there is a specularly reflected proton. Now, I
Cool.
should say about the specularly reflected proton. Um, so in quasi-parallel shocks, what happens is that as shock moves, it has a fluctuating electromagnetic field. So plasma protons, they get reflected by the shock. And when they get reflected by the shock, they produce a current imbalance.
Yes.
And that current imbalance is crucial for driving return current electrons close to the shock foot. And they can also heat the electrons. So
Cool.
we can do a similar analysis like Fourier analysis. And if we and we saw that the mode or electrostatic mode is very similar to what we expect from our analytical um, calculation, which is shown in figure 4. So if you go to the figure 4, we have
Cool.
uh, figure 4, B2, panel B2, we see there is electrostatic mode when there is a specular reflection. And as time evolves, the specular reflected proton, they are swept up by the plasma, by the shock. So you will see that they will disappear. So which you see that in figure B2, the electrostatic mode disappear. So this electrostatic mode appears periodically whenever you have a specular reflection ions.
Bounce, yes.
Yeah.
Hmm, I'm
So
with you.
so far, so far we understood that this electrostatic mode and the specular reflection, superthermal electrons, is a natural byproduct of this current compensation. But now we want to quantify how much heating we expect from this kind of scenario.
Yes.
And to do this, we performed control simulation.
Okay.
So the basic idea of the control simulation is that we chose the beam parameter. The beam means the ion beam, similar to our shock. But since we know that the beam properties depends on the region of interest, so if you are very close to the shock, the beam is expected to be very dense, so you
Yeah.
expect the current to be very strong. But as you go far away from the shock, the beam current decreases, so you expect very dilute beam. So we use both beam parameters to understand how much heating we expect from this kind of scenario.
Cool.
Because our ultimate goal of this paper is to understand the production of the superthermal electrons
Yes.
and, and quantification of the electron heating in the upstream.
Cool. Good.
So if we go to our next section, then we have a setup of control simulation, which is very standard setup we have used in our previous work. So we have a electron proton plasma, we have periodic boundary, and then we have a beam population, and we only change the beam parameter to see the differences.
Yes.
Now, if you go to the figure 5, then
Mhm.
we show a case which represent
Right.
very far upstream of a shock where you have very dilute beam. And in the very dilute beam case, what we found that thermal port. So this, if you in the figure A1 and B1, they shows the initial configuration of our setup. We have a very dilute beam, very thin and dilute beam, and cold dilute beam, and then we have a thermal population, and the color shows you the current different current of by the different population. So
Yes.
this is equal to 0, but at equal to 1, in the panel A2 and B2, we see that the current driving population now has produced superthermal electrons. So initially we do not have any superthermal electrons, but now we have superthermal electrons, which is very similar to what we saw in our shock simulation. Now we
Yeah.
can also obtain the spectra of these electrons. And if we obtain the spectra at different times, this is how it looked like. So if we go to figure D1, figure C and figure D. The figure C shows you the spectrum of electrons and protons at three different times.
Mm.
And you can see the blue solid curve. You have superthermal hump of electrons,
Yes.
which is in our shock simulations as well. And then that hump is actually disappear as you evolve the system longer time because there is energy exchange between the superthermal electrons with the whole population. So the whole population heated up. And
Yes.
you see this the rate curve, the rate solid curve, that shows you that there is a little bit of heating because of this, because it has moved from the initial black location. So which
Mhm.
means that there is a heating of electrons. So now
Nice.
in this case, since the beam is very dilute, we do not expect that much of heating in the very far upstream due to this ion driving population.
But
But if we have a beam which is very dense, then
yes,
that can actually heat the system significantly.
correct.
And before I say anything about that, I would like to draw attention to the figure D. You can see in the figure D, which shows the mode analysis in our control simulation. We also see that the figure D, we have a electrostatic mode which fall exactly at the location where we expect from our analytical calculation.
Yes.
Now, if we go to figure 6, that shows us what will happen if you have very, very dense beam, which
Correct.
represents the location of shock food.
Oh.
Uh, Now, if we, but I should mention at this point that although in our control simulation, we chose different region at like separately, in
Uh-huh.
realistic environments, uh, electrons or background actually exposed to all kind of beam when they move the shock, right? As time evolves, they just move across the shock. So they basically face all the phases of the current. Now, when they reach the shock and they're exposed to very dense beam of current,
Okay.
and in that dense beam of the current, it can experience a significant amount of heating, and this is what is shown in figure 6. So figure 6 is very important. So the vertical axis of figure 6 that shows you the temperature shown by the black curve
Yes.
and black solid curve, and then the electrostatic mode normalized with respect to the beam velocity that is shown by the dotted curve. And the
Yeah.
horizontal axis that shows the time, which is normalized in ion cyclotron time scale, which is the very standard unit in shock simulations.
Yep.
Now, what you see in the black curve that there is a sharp rise at t very t close to zero region.
Mm.
Black dotted curve, we see there is a sharp rise of electrostatic mode. So what happened is that plasma generally don't like current imbalance. So if you have a control simulation, and if you just have a current, plasma don't like it. So it will just oscillate at a phase. So there is a transient phase.
Yes.
The moment you cross the transient phase, you enter in the linear growth phase, and that is the exponential phase. And you can see the exponential phase starts at somewhere. Uh, okay, so it start just after the transient phase, and
Right.
then the amplitude of the electrostatic mode increases, and then after certain point, it start decaying.
Yes.
Now, if you look at this temperature, which is normalized with respect to the initial temperature, you
Yes.
see that initially the temperature is close to 1, so temperature is not changing.
Right.
Then the temperature started increasing, and so it shows you there is a transformation of energy from the electrostatic mode to the
Yes.
temperature.
Uh-huh.
And the red and the blue vertical lines that mark the region where we did the analysis, which is shown in figure B and C. So
Okay.
in figure B, the blue curve that shows you that superthermal hump of electrons and also protons. And you see in the red curve, which is shows that at much later time, what the distribution of electron look like, and you can see there is much more heating than what we saw in our previous figure. In previous figure, we saw very little bit of heating, but now we have significant amount of heating. And in figure C, we also see there is a, similar mode, which we expect from analytical calculation. And also at the late time, the electrostatic mode disappears. And all of this happens within very short period of time, like within 2 ion cyclotron time, which is
Okay.
a typical time scale over which you expect the specular reflection. So in that, you do not have much amount of time. So if this heating is really slow, then it is not so effective because the shock will sweep up the plasma and electron will not experience this. But
Yep.
since this heating time scale is really short, electrons actually can get much heating from this kind of mechanism.
Very nice.
Besides to heating mechanism, I should mention there is another type of heating mechanism which can happen at the shock precursor, just ahead of the shock foot, which is called the non-resonant heating, which happen due to the fluctuating electromagnetic field. They can
Yep.
also be plasma. So there is various sources of heating in the plasma, but this heating cannot be ignored. What we found from this paper, which is extremely crucial. Now
Correct.
we can actually estimate the ratio of the beam velocity to the thermal speed of the electrons, because that is a quantity which is equivalent to the Mach number of the shock. So the Mach number of the shock is defined by the velocity of the shock divided by the thermal speed. Now, the beam velocity is very comparable to the velocity of the shock. And this is what we showed in figure 7. So in the vertical axis, that shows you the ratio of the beam velocity to the thermal speed of electrons.
Yes.
And horizontal axis that shows you different simulations.
Okay.
Empty symbols that shows the initial ratio of beam velocity to the thermal speed of the electrons.
Okay. Okay.
Solid that represents your the final temperature, the final ratio.
Right. Right.
Now, the figure we just discussed in figure 6,
Mhm.
we that is represented by, I mean, if we can do a quick estimate. So we see the temperature is raised by a factor of 9. So that means that thermal speed of electron will increase by a factor of 3.
Correct. Yep.
So if we have a beam to thermal speed ratio 6, then the beam to thermal speed ratio will drop by a factor of 3, so it will become 2.
Okay. Yes. Uh-huh.
And this is what we showed in figure 7. So if you look at figure 7, the first symbol that shows you the initial ratio, empty circle, empty star mark, that
Yeah.
shows you that is 6, and then it drops to 2. We
Hmm.
did this experiment for different parameters,
Okay.
and each of these empty symbols that represents the effective Mach number of the shock to begin with. At the
Hmm.
final stage, it shows you that the Mach number drops, and because you heat the plasma.
Yes.
And interestingly, we see there is a kind of universality in the heating. And
Correct.
in all cases, you see the effective the ratio is smaller than 3. And this is actually a very important point. What it tells us that the superthermal electrons or return current electrons uh, at close to the shock foot, they have effective temperature such that their effective Mach number is below 3, which is sort of universal and does not depend on the initial uh, beam to or the initial Mach number of the shock.
Beautiful.
Now, from this, we can actually do various things because uh, there is a well-known problem in the literature how electrons get injected into diffusion shock acceleration because the
Okay.
criteria that how electrons accelerated or injected into diffusion is still not well known. And if electrons are much hotter in the upstream to begin with,
Okay.
then this complication to injection into diffuse shock acceleration, it can be quite simple. And what we showed from this figure, from this analysis, that it doesn't matter what is the initial Mach number of electrons.
Yes.
As electron moves close to the shock, they become much hot, and their effective Mach number is below 3.
Yes.
Very important. And
Yes.
it can help us to simplify the process of electron injection.
Cool.
And this is one of the very important point that we obtained from this paper.
Beautiful.
And and now I'm going to talk about a different scenario. So far, what we discussed is um, the quasi-parallel shocks,
Mm.
right? And we saw there's a lot of heating. So naturally, one would ask a question, well, if we have a quasi-perpendicular shock,
Yes.
do we expect this kind of heating or not? So to understand this, we performed another set of simulation now with quasi-perpendicular shock.
Okay.
And the result is shown in figure 9.
Hmm.
So in figure 9, what
Hmm.
we showed is that the distribution function of electrons and protons, similar to what we showed before. But now, if you look at the proton distribution function, that is panel A,
Yes.
you don't see any reflected or energetic population, right?
Yes. Right.
Because in quasi-perpendicular shock, if your magnetization of the plasma is not um, weak enough, it does not reflect proton much. If it
Okay.
does not reflect proton much, then you do not expect any current in the upstream due to the proton. But if you look at this electron distribution, you see there is a reflection of electrons.
Hmm.
And I use the color, the blue color, to represent the current, and you can see there is a reflected population, and there is a current compensating population.
Yes.
Current compensating population is moving towards the shock.
Hmm.
And that's why, since they're moving towards the shock, they have a current which is minus of like the velocity because electron has a negative charge. And that's why is a positive current. So you have
Yes.
like total current is balanced exactly.
Yep. I'm with you.
Yeah. So it shows you that you
Cool.
can have different kind of environments, and you can different environments, you can see a different type of things. But one thing to notice from this figure is that the return current population is not so energetic in this case. And the reason is that reflected electrons are much lighter in mass, so they do not have some kinetic energy. So you do not expect that kind of heating for the reflected population.
Factor
But
18.
this scenario may change if you have very weakly magnetized plasma, because it is recently shown that in a very weakly magnetized plasma, they can also accelerate protons. Because if you, so the idea is that if you keep down the magnetization of the plasma, then at a certain point, the orientation of the magnetic field may not matter much.
Right.
So you expect the scenario may change when if you have very, so these are like the future aspect of this work. Uh,
Cool.
Oh, all right. So I think I discussed quite, I mean, very briefly. There are many things in this paper, but I think I have more or less cover all of the results of the paper. Now, just to take the take-home summary of which I'm going to tell now that so this is the first analysis which actually show the generation of the return current in the collisionless shocks.
Yes.
And what we understood from this analysis that the electron distribution in the in the upstream of a shock, it
Yes.
may not be Maxwellian distribution.
Okay.
So normally we expect the electron to be Maxwellian distribution, but it may not be Maxwellian distribution. It can have a superthermal hump,
Yes.
and that superthermal hump is composed of current compensating electrons, and it can also be compensated. It can also contain some sort of reflected electrons, because the reflected electrons which generate at the shock foot, they can also escape. So it's a very complex environment, and you have both population present in that superthermal electron population.
Nice.
Whatever the population is, the total current in the system is zero, which is very interesting. So plasma managed, so it doesn't like any current imbalance. So it did a great job to balance the current.
Cool.
Secondly, what we found that the heating prescription of electrons, which is sort of universal. So we show that if you have a system where you have a beam current, then the final thermal temperature of the electrons could be equivalent to the beam current, beam velocity of the current driving population. So this is what we showed from this paper.
Correct.
And this paper also tells us that electrons are non-adiabatic across the shock. And this is one of the fundamental assumptions we generally make in many cases, but it clearly shows the electrons are non-adiabatic. So it has a far-reaching implications, in particular to understand the electron temperature in our solar wind.
Right.
Because in our solar wind, we normally see that electrons are much hotter than what we expect from the adiabatic expansion. So this kind of study actually can help us to understand the electron heating in the collision in the solar wind environments.
Very cool.
Yes, yeah, I think I've covered almost. Yeah.
And there's a little bit of an appendix here on the cold beam current, where we have a
Yes. Yeah, so in the appendix, we did a linear analysis of so the equation A1 that shows us the dispersion equation.
yep.
Um, and so if we plot the dispersion equation, we can see figure 10 that shows us the way, when you expect the growing mode, and it tells us that so the vertical axis is the ratio of the beam velocity to the sound speed of the electrons.
Okay.
So this is sound speed, not the thermal speed.
Yep.
And
Yes.
the horizontal axis is the wave number.
Mhm.
And this picture tells us that if you have a beam velocity larger than the sound speed of the electrons,
Sure.
you expect some sort of modes, electrostatic mode. If your beam velocity is less than the sound speed of electrons, then you do not expect any kind of mode.
Nice.
So it's convey the idea that why do we see the electron temperature or electron thermal speed at the late stage equivalent to the beam velocity.
Ah,
So if you have a very cold plasma, you can have a beam. They can actually increase the temperature of the electrons. But if you start with a very hot electrons, you
oh,
may not see that much of heating of electron
sure.
due to the electrostatic mode. But if you have some electromagnetic turbulence, they can still heat the electrons, which we still not well understand that problem.
Very cool.
Yeah, yeah,
Very cool. Very cool. Very nice. Beautiful. Siddhartha, I want to thank you so much for walking us through your very awesome APJ article.
yeah. Thank you very much for the Zoom. Yeah.
Sure. And you touched on it a couple of times there, so let me go ahead and push on it a little bit. Where do you think we go from here, given the published article? There's always more simulations one could run, so let's but in particular, some of the points you mentioned on coming in on the turbulence, things that are not well known. Maybe there's some observations, solar wind, etc., that could help validate, verify some of the results and so on. So just sort of next steps, where do we go?
Yeah, so this is a very important question. So I think that we have a very significant results which can help us to understand the temperature discrepancy in electrons in our solar wind.
Yes.
That can help us, I mean, to improve our model, that we find that electrons are non-adiabatic in most of the cases. The second thing we are quite interesting is that how electrons actually participate into diffusion shock acceleration. And
Yes.
this
Yeah.
is the problem we are right now investigating. And we
Okay.
have very couple of interesting results. So one of the papers we have recently submitted, another one we are working on. So we think we understand how electrons start accelerating at the shock. So which is a very interesting problem.
Indeed.
The second is that, I mean, there can be other problem as well, since we have run 1D simulation. So there is always a question like how much we can rely on this simulation. So
Correct.
one can do a 2D analysis, and I think it will be nice if we can perform 2D simulation or 3D simulation and verify our results.
Yeah.
Uh, there is always something which probably you don't know, the nature of the turbulence, how it work in 3D and 1D. So it's always good to verify from there.
Indeed.
Yeah. And the ultimate goal of this study is to provide some prescriptions of electron heating, electron injection at the shock, and because in most macroscopic world where we do not resolve kinetic scales, we need these prescriptions.
Correct.
And our idea is to provide these prescriptions, and so that people in the galaxy simulations community or galaxy cluster community, they can use our prescriptions for a better control over electron heating and the shock injections problem. Yeah.
These are basically subgrid models within a hydro code or MHD code.
Absolutely.
Yeah.
Yeah.
Yeah. Mhm.
Yeah.
Cool. Very
Yeah.
nice. Well, I really look forward to seeing these next couple of papers come out. It'll be very exciting to see. Be great.
Thank you very much for the meeting. Yeah.
Yeah, thank you, Siddhartha. And that will do, everyone. And I hope this made your astronomy day and your return current day just a little bit better. And we will see you on the next one. Bye-bye.